All right, so this is from the 2010 AP FRQ. It's question number 5. Shh. It's a refraction question and Snell's law. All right, so here's what we have. We got this incident beam strikes this prism, and see how they have the normal line shown here? Whenever you do optics problems, you're measuring angles off the normal line. So they showed normal line there. They got a normal line over here. The problem tells us that the light starts in air. There's a big assumption here. The problem is assuming that we know the index of refraction for air. The index of refraction for air is the same as a vacuum, 1.0. Just real quick, I want to review. The basic definition for index of refraction is C over V, where C is a constant. C is the speed of light in a vacuum, right? And then V is the speed of light in whatever medium you're talking about, right? So dudes, how fast, if you're talking about air, so index of refraction for air, why does the index of refraction for air, why is it 1.0? Because what's the speed of light in air? It's basically C, right? And you get C over C. You know, the speed of light in air is pretty much what it is in a vacuum, okay? So air has an index of refraction of 1.0. If you didn't know that, you're kind of stuck. Now, first question. Calculate the angle of refraction, theta 2, at the left side of the prism. Oh, I want to mention one other thing. This given diagram is not showing the reflection. At each boundary, there's also a reflection, but the diagram doesn't show it. So see, this incident beam comes in. So they're showing the refracted ray into the prism. But just be aware, there's also a reflected ray like that. And then what's the nice thing about reflection? The angle's the same. Okay, and then down here, at this boundary right here, there's also, we got this theta 3. So this, they're showing the refraction, but there's also reflection there. And then that'd be the same angle. Okay, so the first question is super easy. You're just applying Snell's law. They want us to solve for this theta 2 in here, measured off the normal line. So the equation that applies here is Snell's law. N1 sine theta 1 equals N2 sine theta 2. We talked about this on Monday. So we have everything except for theta 2. So sine of theta 2. So this is an FRQ question, so show the substitution. So this is going to be N1 sine theta 1 over N2. So sine theta 2 is going to be 1.0, right? This is going to be our N1. This is our theta 1. This is N2. We're looking for theta 2. Sine of 40, and then N2 is the 1.65. Pretty easy, right? So sine theta 2 comes out as, where did I do this? 0.39, 0.39. So then do the inverse of that, sine inverse, and you get theta 2 equals 22.9 degrees, which is the answer. 22.9 degrees. All right, question B. So using the same prism, describe a change that would result in total internal reflection of the beam at the right side of the prism. Okay, so let's just quickly review total internal reflection. What is total internal reflection? It's basically when you have no more refraction, and it can only happen when light is traveling from inside something, you know, from more dense into less dense. So it would happen at this boundary right here. It would happen right there. So remember, the thing they're not showing is that there is reflection here. There is reflection. This ray strikes that surface from the inside. Some of it reflects and some of it refracts. But can this refraction go away? It can, because what's the largest angle of refraction you could have? What's the biggest possible angle for refraction here? Pretty obvious question. 90. The largest that this could be is 90 degrees. Can it refract beyond 90? In fact, so here's an important term. When the angle of refraction is 90, there's a special name for this incident angle. That angle is called the critical angle. The critical angle is when you're about to lose your refraction. Does that make sense? Okay, so what they want us to come up with is a modification to this situation where we would basically get only reflection at this boundary, no refraction. So what would that require? To have that happen, what would need to occur to make that happen? Well, what would have to happen to theta 4? Theta 4 would have to get what? Bigger, right? Because it's got to go to 90 to lose the refraction. So theta 4 has got to get bigger. So to make theta 4 bigger, what needs to happen to theta 3? Theta 3 needs to get what? How do we make theta 4 bigger? By making theta 3 bigger, right? If this hits, if this gets bigger, if this angle in here gets bigger, so in fact, let me try to show it. It would kind of be like this, like instead of this ray coming down like that, it would need to like hit like that. Like the ray would have to be like that, and then let me show the normal line. Here's the normal line. So in fact, hold on. Sorry guys. I want to make this super duper duper clear. So instead of this situation, so let me erase this, take this away. It would have to be, to get theta 4 to be bigger, it would have to go boom and like hit down here somewhere like that. Here's the normal line, and then, you know, if this angle here got bigger, can you guys visualize this? Then theta 4 got bigger to the point where it could be gone, and then all there is reflection in there. Okay, so theta 3 had to get bigger. That was this angle here. Now, what happened to theta 2, dude? You can see it. What needed to happen to theta 2? Smaller. And then what would happen to make theta 2 smaller? What needs to happen to theta 1? Smaller. Okay? All right. Any questions on this? I think I explained that relatively well. What do you think, McFarland? B minus? Okay, last question. Now, hey, this one here, we're not going to do it. That's called thin film interference. But we can solve this one, the wavelength of the red light in the film. So, okay, what they're giving us here is this situation. So the incident beam is now perpendicular to the surface. So it's kind of like a whole new situation. Let's just get rid of this. Okay, so they give us this whole new situation. So we're looking at, we got this boundary here, it's like this, and there's this film, right? There's this thin film, and the index of refraction for the film is 1.38. Okay, so this area is the film, and then over here is air, right? So the index of refraction for air is 1.00, and what they're saying is the ray comes in like this, perpendicular, bam. Now, dude, what happens to the speed of light when it goes from one medium to the next? It changes. In fact, you can see that in the index of refraction, N is C over V. If the N changes, you know, C is a constant. C never changes. So if your N changes, that means your V changes. When light goes from one medium to the next, it changes velocity. Now, what's the explanation? Why does light change velocity? Well, what's the equation for the velocity of a wave? Wavelength times frequency. So what happens is, as the light goes from the air into the film, well, what's going to happen to the velocity? Is it going to speed up or slow down? It's going to slow down. The velocity decreases. Now, what is the reason for that? Does the wavelength change or does the frequency change? The wavelength changes. In fact, frequency stays constant. For a given ray, for a given light ray, the frequency is constant. So a decrease in velocity means a decrease in wavelength. So what they want us to figure out is the wavelength in the film, right? what's the wavelength inside the film, and we have the wavelength in the air. The wavelength in the air is 6.65 times 10 to the negative 7 meters, right? So how do we do this? We have the index of refractions, and we have the wavelength in air. So the realization here is what? Frequency stays constant. The frequency in the air is the same as the frequency in the film, in the thin film. Does that make sense? So here are the equations. So we're going to need that equation. Velocity is wavelength times frequency. And then we also need the definition for index of refraction. N equals C over V. Okay, so what can we plug in for C? So the index of refraction for the film, is going to be C over V. Well, what's C? That's going to be wavelength in air times frequency in air, because air is basically a vacuum, right? All I did is I took this equation, plugged it in there. And then what's V? That's going to be the wavelength in the film times the frequency in the film. So what do we know about those two frequencies? They're the same, so they cancel. So basically we have index of refraction of the film equals wavelength in air over the wavelength of the film. So the wavelength in the film is going to be index of refraction of film. So this is going to be 1.38 times 6.65 times 10 to the negative 7. And then that gives us the answer, which is 4.8 times 10 to the negative 7. I get the feeling. Oh, did I make an algebra error? Hold on. Oh, yeah. Thank you. Here, let's do that again. Oops. Okay, take 2. So this is going to be wavelength in air over that. So this will be 6.65 times 10 to the negative 7 meters over 1.38. Or you know what, guys? I don't know if that makes much sense. Dude, another way you could have done this is, look, you could calculate the frequency in air. Just go ahead. How would you find what the frequency in air is? You go, velocity is wavelength times frequency. So frequency is velocity over wavelength. What's the velocity of light in air? 3 times 10 to the 8th meters per second. Divide that by the wavelength, 6.65 times 10 to the negative 7. So you go ahead and just calculate what the frequency is, right? And then what's going to be true? That frequency stays the same. So then take that frequency and plug it into the film, but you got to find the velocity in the film, right? How would you find the velocity of light in the film? N equals C over V. So V is going to be C over N. So you go 3 times 10 to the 8th meters per second, 1.38. So find the velocity in the film, right? And then velocity is wavelength times frequency. So you got your velocity, you got your frequency, solve for wavelength. Basically, frequency stays constant.